Okay, man, it's Mr. Ward again. Got problem 43. We'll give this one a shot. It says a circular motion addict of mass 80 kilograms. Let's put that down. Rides a Ferris wheel in a vertical circle of radius 10 meters. At a constant speed of 6.1 meters per second. So V, we'll say VC. Just to remind us, it's constant 6.1 meters per second. What is the period of the motion? In seconds, of course. What is the magnitude of the normal force from the seat when both go through, this is for part B, through the highest part, so we'll say Fn top. And part C says, what is the normal force at the lowest point? So we'll call it bottom. Okay, well, the first part, finding the period, that shouldn't be too hard. We know that the period, that the velocity of something is equal to, in the circular motion, is 2 pi r over t. So the period then is simply going to be 2 pi r over rv constant. So that would give us 2 pi times 10 meters over the 6.1 meters per second. So let's get your calculators and see what we got. Okay, let me double check that. I got 10.3 seconds the first time around. Let me check it again. 2 times pi times 10 divided 6.1 equals. Okay, so that looks good for part A. That would be the period. Now, the next thing we're going to need to do is to draw a free body diagram at the top. So this would be the guy sitting on the top of the Ferris wheel. And obviously, the force acting downward on the person is the weight. And because the person is has a radial acceleration toward the center of the circle, that means that some of the forces in the vertical direction must point toward the center of the circle also. So that tells us that the guy is going to feel a little bit lighter up at the top. And the sum of those two forces then is going to be the radial force. Okay, so sum of the forces equals ma radial. The sum of those forces, using this as the direction of the acceleration toward the center of the circle, you would get mg minus fn equals mv squared over r. And what they want us to calculate then is the normal force itself. So Fn would simply be mg minus mv squared over r. Can I do that right? Okay, so that looks good. So that's going to make him appear lighter because his 80 kilograms times the 9.8 meters per second squared minus the 80 kilograms again times the 6.1 meters per second quantity squared over the radius of 10 meters. That should give us the normal force. Okay, so grab your calculators and let's go. Okay, well, I'm getting 486 newtons. That makes sense because his weight here would be just a little bit under 800. So the normal force you would expect to be less because the vector in our diagram showed that. Okay, so if you understood that, good. If not, a little question mark there so you know to ask somebody about that. Now let's take a look at the bottom. Obviously here we're going to have mg again at the bottom, but because the guy is going from this low place to a higher place, to move him upward off of the horizontal, we're going to need a larger force up, and of course that would be his normal force at the bottom. This one over here would be F normal top. That one. Okay, so we do the same thing we did before. Sum of the forces equals MA radial. And we're going to get, because A radial is going to be in this direction. By the way, I should box these. And make sure your acceleration is on the outside of that box. So we're going to end up then with F normal at the bottom minus mg is going to equal the mv squared over r. And rearranging things, F normal at the bottom would be equal to mg plus mv squared over r. Plugging in our values, 80 kilograms times 9.8 meters per second squared plus 80 kilograms times 9.8 meters. Oh, that's not right. We want the velocity. The velocity of 6.1 meters per second quantity squared over the radius of 10 meters. Get your calculators and see what you get. Okay, well I got 1080 newtons, and again that makes sense. So that should do it for this problem, the Ferris wheel problem. Okay, we'll see you guys tomorrow if everything goes right. And I'm not going to send any more videos right now. I may put some things up tonight if I get any requests from people. So I'm going to shut this video down.